Hey there, and welcome. In the world of engineering, some of the most powerful forces holding everything together are, well, they're completely invisible. So today, we're going to pull back the curtain and actually see them. We're talking about the internal stresses inside buildings and bridges, and we're going to do it using two of the most powerful tools in any engineer's toolkit: shear force and bending moment diagrams. So here's the game plan. We'll kick things off with the big question: what's actually holding a structure together? Then we'll meet our two main characters, shear force and bending moment. After that, we'll get into the rules that connect them, walk through an example step by step, and then bring it all home by talking about why these diagrams are just so incredibly important. Ready? Let's get into it. Okay, so first things first, when an engineer looks at a structure, their main job is to make sure it can take a hit, that it can handle all the weight and forces on it without, falling down. And to do that, they have to understand what's happening deep inside the materials themselves. I mean, really think about it for a second. You walk across a huge bridge, you stand on a balcony, stories up in the air. How in the world are these things holding all that weight? It's not magic, I promise. It's all about physics. And the secret? It's inside things like this, a beam. See, when you put a load on a beam, it doesn't just passively sit there, it actively fights back. It develops this whole network of internal forces, this incredible internal resistance that perfectly cancels out the external load and keeps everything standing. And our job is to figure out exactly what those forces are and where they're strongest. So, to understand that internal fight, we've got to meet the two key players in this whole story: shear force and bending moment. Think of them as the two main ways a beam resists all the crazy stresses happening inside it when it's under load. First up, we have shear force. The best way to think about shear is to imagine cutting a piece of paper with scissors. That slicing action, that's shear. Inside a beam, shear force is that internal force trying to make one slice of the beam slide vertically past the piece right next to it. It's the beam's direct reaction to any up or down forces. And our second key player is the bending moment. So if shear is all about sliding, bending moment is all about turning. It's the internal twisting or rotating effect that makes the beam actually bend and flex. This is the force that puts the top of the beam in compression and stretches out the bottom in tension, or vice versa. And here's a super simple way to remember how this works. By convention, if a moment makes the beam sag downwards, kind of like a smile, we call that a positive moment. But if it makes the beam arch upwards or hog, like a frown, we call that a negative moment. Just remembering smile versus frown tells an engineer instantly where the dangerous tension forces are, which is absolutely critical for design. All right, so we know what shear and moment are, but how do we actually map them along a beam? Well, turns out there's this really elegant, almost beautiful mathematical connection between everything. Let's dig into the rules. It really all boils down to these two little equations from calculus. The first one basically says that the slope of the shear force diagram at any point tells you exactly what the load is at that point. And the second one? It says the slope of the bending moment diagram is simply the value of the shear force. This is huge. It means these diagrams are fundamentally linked. If you can draw one, you can figure out the other. And check this out. This table shows you the practical result of those rules. The kind of load you have directly tells you the shape of your diagrams. A single sharp point load gives you a flat line or a step for shear, and a straight sloped line for moment. A nice, evenly spread out load gives you a sloped line for shear and a smooth curve, a parabola, for moment. It's totally predictable, which is exactly what engineers love to see. Okay, theory is cool and all, but let's make this really sink in. We're going to take a super common example and build both diagrams from scratch, step by step. All right, here's our setup. We've got a beam that's just resting on two supports, one at each end. And right in the middle, we have a single force, which we'll call P, pushing straight down. This is like textbook problem number 1 in structural analysis. So step 1, and you can never, ever skip this, you have to figure out the reaction forces from the supports. For this beam to not go anywhere, the supports have to push up with the same total force that the load is pushing down. And because our load P is dead center, the math is easy. Each support just takes half the load, so P divided by 2 on each side. Awesome. Now we can draw the shear force diagram. We start at the far left. The first support reaction immediately shoots the shear value straight up to P over 2. Then, as we move to the right, nothing's happening, so the shear just stays flat. Until, bam! Right at the center, that big downward load P kicks in and drops the shear value way down. It stays flat again until we hit the very end, where the final support pushes it right back up to 0. Perfect. the diagram closes. And now for the bending moment diagram. All we have to do is remember our rule. The change in the moment is just the area under the shear diagram. So that first positive rectangle on our shear diagram, that creates a steady, straight line increase in our moment. Then that second negative rectangle in the shear diagram creates a matching steady decrease, bringing the moment all the way back down to 0. We end up with this perfect triangle shape. And here it is. This is probably the single most important lesson from all of this. Take a look. Where's the highest point on our moment diagram? It's right in the middle, exactly at the spot where the shear diagram crosses the 0 line. This isn't a coincidence, it's a fundamental rule, and it's how engineers find the absolute most dangerous point of stress in any beam. Okay, so we've drawn some pretty charts, they look neat, but so what? Why does this actually matter in the real world? This isn't just some homework problem, right? Right, because these diagrams aren't just an exercise. They are the engineer's blueprint for a safe and efficient design. They tell you precisely where the beam is being stressed the most. That, in turn, tells you exactly how strong that beam needs to be and how big it has to be. It lets you use just enough material, not so little that it's dangerous, but not so much that it's wasteful and expensive. At the end of the day, these diagrams are what make sure our structures are safe and reliable. So the next time you walk across a bridge or you see a skyscraper going up, you'll have this new superpower. You'll be able to literally visualize the invisible forces of shear and moment flowing through its skeleton, which kind of leaves you with one final question to think about. What other invisible forces are out there, constantly shaping the world we all live in?